So let's see how we're doing. Let me just share the screen here. We had started magnetostatics last time, and the purpose of today is really to make hopefully very good progress on this. Essentially today it's almost a kind of fresh start, because we had exchanged some notions about this before, but today we're actually going to start with something that falls essentially from the sky, namely from experiments around the 1820s. And this was about the understanding that in addition to the electrostatic fields that were around, there was another thing floating around giving a force that was transverse when currents were passed through various wires. So they had lots of really clever little constructions where they would bend pieces of metal wires like this, then draw a current in them, and then see how that would apply a force onto that. And out of very basic experiments, they summarized all these experimental results in one law, which is the Jean-Sebastien law, which will be our starting point today. So you really have to view this at this point as an experimental fact. Okay, it's really an observational fact. And what does this thing tell you? Well, it tells you that if you were to have a certain amount of current, say you've got a little, piece of wire like this carrying a certain amount of current in a certain direction, and you were to put an observation point somewhere in space here, you would feel an object, a magnetic field at this point coming from this here. And the size of this field, the size and orientation of this field is given by the following formula. So B measured at this evaluation point R is some proportionality constant, mu0 over 4 pi. I'll have a little bit more to say about this mu0. So it's called the vacuum permeability. It's just a number at this stage. But now, if we imagine that we've got a current going through a certain loop in here, the total field viewed at R is an integral over this this loop here. So I imagine that this thing kind of carries on in a certain shape or form like this, and I'm summing little length elements BL on this loop here, on this path. So this would be path P. And at each position that I have for my source here, call it BL prime, I have a certain current going through, which is a vector. So this one carries the direction in space. And the relationship with the distance that we have looks like this. So it's very similar to what we had before. Okay. And if you look a little bit at the way the cross product works, the right-hand rule comes in handy at this stage. So for example, if I have a current going in this direction here, and then the R minus R prime vector is then this vector here, right? That's R minus R prime. So my field would be coming out of the page here. So I would have this field going out of the page like this, okay? Just like right-hand rule. So observational fact, Jean-Sebastien law. I don't know if you already knew this this name here. I presume that you have been parachuted this law in your first course, also in the first place. Okay, so that's the kind of historically accurate way of introducing the notion of the magnetic field here. We've already talked about the Lorentz force. This predates the Lorentz force, like this. Okay, so you've seen Jean-Sebastien before. You haven't? Okay, very good. So now you see, like, democracy reigns, everybody's back at the same point. You have now all seen Jean-Sebastien like this. There's a completely different way of introducing the magnetic field as an inevitable consequence of special relativity. We'll get back to this discussion later on in a few lectures. For the moment, however, I've still elected to follow the more historical path of saying that there were these people in laboratories all over the place that came up with these notions and quantified what this field was. Okay, so that's what it is. Okay. Now the mu0, that's the fun thing that deprecates all the books from more than about 5-6 years ago. The value of mu0, it used to be just 4 pi 10 to the minus 7 Henry per meter. Now it's become actually an observational constant. So you know, in the International System of Units, that's been changed. So, but I've made these jokes before. Okay, so that's just the start here. Now, of course, for the magnetic field that we have here, the principle of superposition also applies, as for the electrostatic field that we have. Therefore, if I had a very complicated collection of currents moving around my space, I could still compute the magnetic field simply by composing this equation as much as I would need to. In particular, so imagine that I have maybe a situation where I've got lots and lots and lots of charges flowing around in space, okay, in a volume. So I would imagine that I've got a big blob of matter, and throughout this blob of matter, there are currents flowing around at intensities and directions that depend on the place at which I'm looking. Okay, so that defines for me, you remember the current density J that we had before. So for example, if I have a volume source of magnetic field, say that I've got a big blob, you know, it could be a big donut of something in which currents are flowing left and right, then of course the magnetic field in this is just going to be given by the volume integral of this current density with the right factor. So again, mu0 over 4 pi. Now I'm going to do the integral over the whole volume. But now instead of just I here, I will put the full current density. All right, so this one is of course evaluated at r prime, and then it's the same spatial factor as we have above. Sorry. So r minus r prime divided by r minus r prime. Okay, so that's a form which is perhaps the most handy, because all other forms can in fact be derived by this. If you have a single wire, then your current density is really like a delta function. It's zero everywhere except along this little wire there. You have situations also where you have a sheet conducting current, and then instead of having a 3-dimensional integral, you do a 2-dimensional integral, but then you would have a surface current density. Okay, so you might see some of these equations later. Okay, so so that's the kind of way it goes. Okay, now there are countless examples of calculations of magnetic field starting from the Biot-Savart law. We could really spend a whole course trying to you know, refine that skill. However, it's a very limited interest in view of some of the other equations that we're going to see later. There is one example, however, which I think is kind of a good starting point, which I've actually written up here, and we'll walk you through it in a couple of minutes. What is it? It really is the absolute Drosophila of Biot-Savart, the very simplest thing you can think of. It's one straight wire. Okay, so one straight wire. Here you see the wire here, this wonderful line, carrying current I. And for the moment, I've got a finite segment because we're going to do the integral like the hard way. So what do I have? I have my wire here at a certain position, and I define my observation point R somewhere away from it. And the point that I'll integrate, as usual, will be this R prime. And now I'm just going to integrate over this line here to get the formula for the magnetic field. So first of all, I want to ask myself, which way does the field point? Once again, the right-hand rule comes in handy. If my current is going to the right in this thing, then when I do the current cross the displacement vector, I get a vector pointing out of the wall. Okay? The intensity of that contribution from the little segment here, well, we have to, we just have to, you know, work it out in detail. Okay, so Let me just get. Okay, so how do we do that? So I have this little distance here. So I define the angle theta here, and then the L prime here that I have in this distance is really just the tan. So this is a tan of theta. So you just like choose your favorite variables in here. I'm going to integrate over this this position L here, but really transform it into an integral over the angle theta that is going to span me from the beginning of the wire up to the end of the wire. At the end, we're going to put theta from minus pi over 2 to pi over 2 to get an infinite wire. Okay, just a little side note. Of course, in a finite wire like this, to have a steady current would be unphysical. I would need to pump in charge at one end or the other. So the calculation is only going to make sense when the wire becomes infinite. I emphasize Biot-Savart here, it's a formula that is applicable for steady currents. We don't want currents that are, at this point, time dependent. We're just going to consider that all these things are steady in time. There's charge moving, but the value of the currents are constant in time. Okay, so that's what it's applicable to. Okay, so I mean, maybe we can go through this quickly. You just write the element here. It's just the distance r with the tan of the angle. That means you can write the differential distance here, just taking the differential of the tan gives 1 over cos squared, etc. And then you can rewrite the distance r minus r prime also as a relationship between the r here, the cos theta you have here, and the full distance r minus r prime here. So said otherwise, you just plug all of this into Biot-Savart. You've got the DL, you've got the current, you've got the cross product, and essentially all these elements are explicited here. So first of all, from the cross product itself, there's a cos theta coming here because of course the cross product is going to be maximal for right angles between the two, which corresponds to theta is equal to 0. And then there's the 1 over r squared, which is really coming from this equation here. So I just kind of write it as cos theta over r squared. And then the DL, we just explicit it like this. And then it becomes just a basic integral because it's only simple integral in theta. The r just goes out of it. It doesn't participate in here. And you can just explicitly compute this integral, just the difference of the signs. And then once again, when you take the limit of angles from minus pi over 2 to pi over 2, meaning that you're looking at an infinite wire going left and right, then you find a value for the magnetic field, which is given by mu0 times the current divided by 2 pi times the distance. In here, now I just switch back to like cylindrical coordinates around this. It's in the circumferential direction around the wire. Okay, so this phi hat is just that one. Yeah, you see what I mean? Okay, so the one really in the original thing coming out of the page here. Okay, so that's the way you would use Biot-Savart to do this. And then I could give you a very, very complicated configuration here. I could give you lots of little currents here and there, going and then say calculate the value of the magnetic field. And in principle, you would be able to do that. But you know, it's a bit of a pain sometimes. Question in the back? Yeah, so essentially here the dependence scales like 1 over r squared. So it's r vector divided by r length cubed. So you can replace it by, if you want, r hat, or r minus r prime hat, unit vector in the direction r minus r prime, divided by the square of the distance. So when I replace the cross product with this cosine here, essentially that's what I've done. There's you just have the scalar distance. It goes like 1 over the scalar distance squared, which is what you have here, right? So as usual, it's a bit, it plays with your memory because you always see 1 over r cubed but it's not R cubed, it's R squared because there's an R at the top, which you can choose to put only unit vectors at the top, and then you have that. Okay. Okay, so that's the way it is. We will rederive this equation in a much simpler way in just a few minutes in any case. Okay, so that's the statement from Jean-Sebastien.